The word trigonometry comes from two Greek words, trigonon for triangle and metron to measure. Bartholomeus Pitiscus introduced the word in this book, published in 1590. The subject itself evolved from ancient astronomy. Because early astronomers thought planets moved in circular orbits, they became interested in chords of circles. The Greek mathematician Hipparchus is called the father of trigonometry because of his treatise on chords of circles written in 150 BC. This work is now lost, but many of the ideas survived in Ptolemy's Almagest, written some 300 years later. Johannes Kepler used trigonometry in the early 1600s to reveal the secrets of the heavens. Kepler constructed a network of triangles to determine the orbit of planet Mars around the Sun. The orbit was not a circle as he had expected, but an oval curve called an ellipse. Trigonometry is widely used today, not only in astronomy, but in large-scale construction, in navigation, and in surveying. One of the major triumphs of trigonometric surveying was finding the height of the world's tallest mountain. It was named after George Everest, who led a British expedition to lay out a huge network of triangles across the face of India. Later in this program, we'll learn how this was done. Every triangle has 6 parts, 3 angles and 3 sides. Trigonometry tells us how to find all of the parts if only some of them are known. For example, in an earlier program, we learned that the sum of the angles in any triangle is a straight angle, or pi radians, no matter what shape the triangle has. Therefore, if you know 2 angles, you can calculate the third angle. If you know all 3 angles and nothing else, you know the shape of the triangle, but you don't know its size, so you can't determine the length of any side. In this program, we'll learn that if 3 parts are given and at least one of them is a side, then we have enough information to find the remaining parts. There are 4 different cases to consider. When we know angle, side, angle, side, angle, side, 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 angle, and side, side, side. The sine and cosine ratios provide the key that unlocks these problems. Remember, the sine of angle t is the ratio of the opposite side to the hypotenuse, and the cosine of t is the ratio of the adjacent side to the hypotenuse. We'll use these ratios in the following form. In this right triangle, the hypotenuse has length h. The side opposite angle t has length h times the sine of t. And the side adjacent to angle t has length h times the cosine of t. When h equals 1, this side is sine t. And this one is cosine t. Remember the Pythagorean theorem? It's proposition 47 in Book 1 of Euclid's Elements. In any right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. Here's a simple proof. Place a square on each side of the right triangle. The area of each square is the square of the length of the corresponding side. Starting from the right angle, draw a line perpendicular to the opposite side and extend it to divide the large square into 2 rectangles. Euclid's idea was to show that this square and this rectangle have equal areas, and this square and this rectangle have equal areas, and here's why. All these parallelograms have the same base and altitude, so the area of this rectangle doesn't change if we shear it like this, or if we rotate it through a right angle and then shear it like this. Therefore, this rectangle and this square have equal areas. And the same is true for this rectangle and this square. So we see that the sum of the squares of the two legs is indeed equal to the square of the hypotenuse. Here's a variation of this proof that does not use rotation. First, shear, just as before. Now translate instead of rotating. Then shear in this direction. Do the same for the other rectangle. And the Pythagorean theorem is proved once again. The Pythagorean theorem reveals a new connection between sines and cosines. In this right triangle, the hypotenuse has length 1. If this angle is t, this leg has length sine t. And this one has length cosine t. The Pythagorean theorem tells us that cosine t squared plus sine t squared is equal to 1 squared. This equation is usually written this way: cosine squared t plus sine squared t equals 1. It's called the Pythagorean identity, and it's true for any angle t. We can also visualize the Pythagorean identity by looking at the graphs of sine squared and cosine squared. Sine squared looks like this. Even where the sine is negative, sine squared is positive and lies above the axis. And cosine squared looks like this. The graph of the sum is a horizontal line of height 1. Because of periodicity, the Pythagorean identity is true for all values of t. Let's look again at the Pythagorean theorem. Something interesting happens if we change the right angle. Keep this side fixed, but move the opposite vertex up or down along this perpendicular line. As the vertex moves up, the angle decreases, but both a and b increase, so a squared plus b squared is greater than c squared. When it moves down, the angle increases, but both a and b decrease, so a squared plus b squared is less than c squared. There's another way to look at this by thinking about our proof of the Pythagorean theorem. These two rectangles fill the square of area c squared. And for a right triangle, they fill the two squares of areas a squared and b squared. Now look at a non-right triangle. As the opposite vertex moves up, you can see that the two rectangles won't completely fill the smaller squares. So c squared is less than a squared plus b squared. And if the vertex moves down, the two rectangles stick out too far, so c squared is greater than a squared plus b squared. Move the vertex up, so c squared is less than a squared plus b squared. The brown regions represent the difference in areas. We can find this difference by using shearing and rotation. Shear, rotate, and shear again. If this were a right triangle, the green region would fill the square exactly. But in general, you get two green rectangles of equal area. And the same is true on the other side. If you shear, rotate, and shear again, you get two blue rectangles of equal area. Now take this brown rectangle, shear it, rotate it, and shear again, and lo and behold, it fills the other empty rectangle. In other words, the two brown rectangles have equal areas. And this is true for triangles of any shape. Right triangles occur when one of the colored regions shrinks to 0. Now let's calculate the areas of the two brown rectangles in terms of the sides and angles of the triangle. The area of a rectangle is the product of its edges. This edge has length A. What about the other edge? Remember, in a right triangle, the leg adjacent to angle C is the hypotenuse times the cosine of C. So the area of this brown rectangle is A times B cosine C. And the area of this brown rectangle is B times A cosine C, which of course is also AB cosine C. So we have found that A squared plus B squared minus two rectangles of area AB cosine C is equal to C squared. We've discovered the law of cosines. It says the square of one side of a triangle is equal to the sum of the squares of the other two sides minus twice their product times the cosine of the angle between them. We've proved it when this angle is smaller than a right angle. When it's equal to a right angle, the law of cosines becomes our old friend, the Pythagorean theorem. And when the angle's greater than a right angle, the same formula works, even though we must add something to A squared plus B squared. How much do we add? One side of the green rectangle is A. To find the length of the other side, look at the triangle above it. This side has length B times the cosine of pi minus C. But if this is C, this is cosine C. This is pi minus C. So the cosine of pi minus C is the negative of cosine C. But that's a positive number when C is greater than a right angle. So the area of the green rectangle is the negative of AB cosine C, which is a positive number. That's also the area of the blue rectangle. And we end up with the same formula as before. And the cosine, positive or negative, tells us whether to subtract or add areas. Finally, there's a corresponding formula for each of the other two sides. Here's a different way to discover the law of cosines. Divide this triangle into two right triangles. This right triangle has base A cosine C and altitude A sine C. This one has the same altitude, but its base is B minus A cosine C. Now apply the Pythagorean theorem to this right triangle and do a little algebra. Square the binomial. Square the first two terms and remove the common factor. Apply the Pythagorean identity and we find the law of cosines once again. Each form of the law of cosines relates 4 of the 6 parts of a triangle, 3 sides and 1 angle. So if you know 3 of the 4, you can find the 4th. For example, if you know 2 sides and the angle between them, the law of cosines is just what you need to find the 3rd side. It can be used to find distances that are otherwise inaccessible. If you know all 3 sides and you want one of the angles, the law of cosines helps here too, but you have to do a little algebra. The cosine of an angle is a number lying between -1 and +1. So if you get a value for cosine C outside this range, that means there's no triangle having those 3 sides. This way of determining angles is especially helpful when use of a protractor is inconvenient. If we know two sides and an angle opposite to one of them, we can find the other side with the law of cosines. But this requires solving a quadratic equation. In a moment, we'll learn another way to treat this without quadratic equations. What if we know all three angles and one side? The law of cosines doesn't help here at all, because there are two unknowns in the equation. To find the other side, we need a new tool called the law of sines. We can discover the law of sines from one of the diagrams used earlier. Divide this triangle into two right triangles. In this right triangle, the altitude is A sine C, and in this one, it's C sine A. So A sine C equals C sine A. The same reasoning gives us two more equations. The three equations can also be written this way. This set of equations is called the law of sines. It tells us that in a given triangle, the length of any side divided by the sine of the opposite angle is constant. This constant ratio has an interesting geometric meaning. It's equal to the diameter of the circle passing through the three vertices. In a later program, we'll see why. Each equation in the law of sines relates four parts of a triangle, two angles and two sides. So if we know three of the four parts, we can find the fourth. For example, suppose we know this side and these two angles. First, find the angle opposite the given side. Now, use the law of sines twice to get the other two sides. In this example, we know two sides and the angle opposite one of them. The law of sines tells us that the sine of angle B is equal to the ratio B sine A divided by A. The numerator represents this distance. If A is smaller than B sine A, the ratio is greater than 1, and there's no possible angle B. If A equals B sine A, angle B is a right angle. If A is greater than B sine A, there can be two possible supplementary angles B. And if side A is greater than B, there is only one possible angle B. Finally, if angle A is greater than a right angle, there is at most one angle B. Now we know two angles and a side between them, and the problem is just like the first example. To make a map like this, surveyors build a network of thousands of triangles, as shown here. They start with a carefully measured baseline, forming one side of a triangle. Angles to the opposite vertex are measured by a precision instrument, like this theodolite, which is part protractor and part telescope. The lengths of the other two sides are calculated from the law of sines. Each calculated side is taken as a new baseline, and the process is repeated over and over. This is called triangulation. To improve accuracy, overlapping triangles are used to form belts of quadrilaterals. Triangulation determines the longitude and latitude of thousands of points in the network. Elevations above sea level are found by a different method called spirit leveling. A vertical rod is placed at a known elevation. A second rod is placed nearby. Each rod is observed through a telescope, and the difference in elevation is recorded. The first rod and the leveling instrument are moved forward, and the process is repeated thousands of times to establish the elevations of critical points along the survey route. Primitive methods of surveying can be traced back to ancient Egypt. The earliest known book on surveying was written by Hero of Alexandria, an outstanding Greek scientist who flourished around 100 AD. His treatise on the dioptra describes an instrument of Greek origin used for leveling and for measuring angles. After the magnetic compass and the telescope were developed many centuries later, the Europeans produced greatly improved surveying instruments, such as this early version of the theodolite. Surveying by triangulation was first described in this book, a collection of maps produced shortly after Columbus launched the great voyages of discovery. One of the great mapping efforts of all time was the Survey of India, which took more than a century to complete. It changed the world's view of India from this earlier distorted version to this more accurate shape. A British major, James Rennell, began surveying the coastline and the southern provinces in 1763. 40 years later, a second expedition, led by William Lambton, pushed the survey 1,000 miles north into the uncharted heart of the subcontinent. Exhausted by 17 years of continuous effort, Lambton died in his tent. He was succeeded by George Everest, a young, ambitious captain who undertook the task with fanatic devotion. For 25 years, Everest led an expedition through difficult terrain, fighting poisonous snakes, tigers, and the deadliest enemy of all, the malaria-bearing mosquito. With the snow-capped peaks of the Himalayas within view, poor health forced Everest to retire to England. Andrew Waugh extended the survey to the border of Nepal to find it closed to foreigners. In 1849, Captain James Nicholson trained his theodolite on a distant summit, called Peak 15, from 6 stations on the Indian Plain. The distance from each station to a point directly below Peak 15 was found by horizontal triangulation. And the theodolite was used to measure vertical angles. By averaging the 6 measurements, they calculated the height of the summit to be 29,002 feet, the highest mountain on Earth. It was renamed Mount Everest to honor the man who played such a major role in the great Trigonometric survey. A Chinese expedition made an independent survey from the north and arrived at the same height for Everest to within a few feet. In the 20th century, 10 different expeditions attempted, without success, to climb to the summit of Mount Everest. Finally, on May 29, 1953, Tenzing Norgay from Nepal and Edmund Hillary from New Zealand became the first to reach the top of the world. In recent years, orbiting satellites and broadcast radio signals established relative distances and altitudes of receivers on the ground with great accuracy. The use of satellites has verified that the traditional method of surveying with theodolites and spirit levels is extremely accurate. New measurements have established the height of Mount Everest as 29,028 feet, only 26 feet higher than the original calculations. But the story is not over. Because of continuing movement of the Earth's surface, the height of Mount Everest could be changing with time. In this program, we've developed 2 properties of sines and cosines that help us determine all parts of a triangle when 3 parts are given and at least one of them is a side. The law of cosines relates the lengths of the 3 sides and one angle of any triangle. The law of sines states that in any triangle, the ratio of the length of a side to the sine of the opposite angle is constant. We've seen how the sine law is used in surveying by triangulation. The next program will discuss addition formulas for the sine and cosine of a sum of two angles. These formulas show that a sine wave combined with a cosine wave of the same frequency is another sine wave, possibly shifted. This fact plays an important role in the study of vibrating motion. Machines executing repetitive motion dominate our way of life. Periodic phenomena are present throughout the universe, from the atomic scale to the solar system and beyond. The ability to analyze all these phenomena using sines and cosines is a major achievement in mathematics.